Can you feel the wind blowing? Shh. That's because it's Global Wind Patterns Day. Let's go. So we have learned about convection currents. These happen because the sun hits the ground and creates these warm, uneven spots. So those warm ground areas, they're going to heat up all the air above it. And as we know, hot, warm air is going to rise. Then it's going to raise to the top, cool down, precipitate, then causing it to become less dense and drop to the bottom. So, just a very important thing for us to remember is that hot air goes up, cool air comes back down. Now, these can be super tiny. It could be the size of like a little parking lot, or as discovered by a guy named Hadley, these can be massive and cover entire planets or parts of the ocean. That's what we're going to look at next. Now, as we know, it is warm down by the equator. And if we take the same perspective of warm air causes air to rise, cool air causes air to sink, we actually realize that we have these same convection cells that are happening within the troposphere and this massive global scale. So down by the equator, we know it's warm, so it's going to cause that air to rise. Then it's going to move up towards the poles, where it's going to cool because we're at the poles now, because the poles don't get as much sun energy as the equator does. So that air is now going to drop, and then we're going to see this air flow back down to the equators, rise up, continue over and over again. These are called Hadley cells, and they happen both in the northern hemisphere and in the southern hemisphere. We can see another example. Hot air rises by the equator, it drifts down towards the poles where it sinks, and then moves again across the surface of the earth, back up to the equator. This is what everything would look like if we did not have spin and we didn't have continents. Unfortunately, we have both of those, so that changes a lot of different things. So instead of having just this one large, what we're going to call Hadley cells, we've actually realized that we have 3 of them on each half of the planet. So if this is our equator here, we remember this is a low pressure system because air is rising. So the air is going to lift up because it's warm, move to a colder area, become more dense, and then drop again, causing surface winds on the earth. We're seeing this in a Hadley cell, which is in between the equator and 30 degrees, in a Ferrel cell, which is between 30 and 60, and then as a polar cell all the way up north. So these 3 on each hemisphere have been developed, and we kind of have noticed this trend and how the air moves in each of these 6 total sections. So let's get a little bit more detail on these. So in the Hadley cell, as I've mentioned before, the air is going to rise at the equator. Then it's going to move upwards to about 30 degrees where it's going to sink. Boom. And then from there, come back down. Ferrel cells, we're going to skip for now. We'll come back to those a little bit later. Now, if you notice, our Hadley cells, the air is moving away from the equator, and then the surface air is moving towards the equator. This is the same thing that's happening up in the polar cell again. We're going to have warmer air than the North Pole, rise up, move towards the North Pole, where it's going to cool, drop again, and then come against Earth's surface. So you can see that both of these are moving in this direction. However, the Hadley cell is much more vigorous, much more powerful. So now let's talk about the Ferrel cell. The Ferrel cell's in this weird spot. So you have to think about it this way. The air that's coming back down, hitting a warmer area, has to rise eventually. So it's going to rise right here, but it's going to rise in both sides of this cell. Going to rise up. And then air that's right here that's coming in this direction is going to have to fall down because it's lost its moisture. It's very dry, so it's going to come down. So it's also going to come down in our Ferrel cell. So if you can figure out the Hadley cell and if you can figure out the polar cell, you can figure out the Ferrel cell as well. Now, as we have put into our brain, we remember that when we have air rising, this equates to moist air and it's going to rain. That is why along the equator, we're going to have a lot of rain, lots of rainforest. So because of these Hadley cells, we see a lot of rain at the equator. But then this air has risen up, it has lost all of its moisture, and now it's traveling north where it's going to sink eventually. But this sinking air, if we remember, sinking air causes high pressure systems. And there's very little moisture in this sinking air. So therefore, at 30 degrees, we see deserts that are forming. And it's all based on this high amount of strong heating that is happening at the equator. So again, here's a great way to look at this. Here's my equator, super important. The equator is where we have the most heating, and you can see therefore it's going to have a lot of rain. Wow, look at this. All of this here is rainforest. So it does, and you're like, oh, this makes sense, Miss Clark. But then as my hot air rises and rains, by the time it gets up to 30 degrees, it's very dry. And this high pressure system up top at 30 degrees with very dry air is what causes deserts to form. And we have it both 30 degrees north, but we also have it 30 degrees south of the equator. We're also going to see deserts forming down here. So as we mentioned, if the world did not spin, our winds would move in this direction. They would be pulled up, and then the surface winds would move down. They'd be pulled down, and the surface winds would move up. So we would see this vertical movement of surface winds. However, it doesn't work this way because the world does spin. And because of this spinning, we actually have all this wind being deflected in the westerly way. So instead of going vertical, because of the spin, these are going to curve westward. That is super important. We need to know that the Hadley cell air is going to move west, and that's because of the Earth spinning. So you can see what this all looks like. Now let's talk about the areas that we need to just quickly memorize. We need to remember that at the equator, winds are moving west. However, once we pass our 30-degree line, those winds are actually going to move east, both in the southern hemisphere and the northern hemisphere. All of this is due to something called the Coriolis effect. You don't need to understand this. It's a lot of physics that's related, but it has to do with the rotation speed on different sections of the Earth. For example, the air at the poles is only moving about 0 kilometers per hour. That means you could stand in the exact same spot and you are just going to rotate around. However, if I am down here, I am moving 1,650 kilometers an hour. Now, interesting, if you go back to the days when people would hop on boats without engines and just sail to go see what they could find, Christopher Columbus, Marco Polo, they had to sail across the ocean, and they would use these Hadley cells as a way to cross this massive ocean. Now, as I mentioned before, when we're looking at our Hadley cell, which is from 0 to 30 degrees, those wind patterns are going to move to the west on both sides. So if I'm a sailboat and I want to get from over here to over here, all I have to do is drop downwards, and then those winds are very powerful, are going to blow me all the way across. This happened all the time in the Atlantic, where we have very similar Hadley cells. It was very easy to go to the west. It was a lot more difficult to go back to Europe. In between our 30 degree and our 60 degree, that air is moving to the east. It's aiming to the east. Again, because these differences in rotational speeds that are happening in different spots. So these Ferrel cells, which are the ones that are moving to the east, they formed these prevailing winds known as the prevailing westerlies. Now you may say, but Miss Clark, they're headed to the east direction. Why are they calling the westerlies? Well, that's because the air is coming from the west to the east, which is why they called it the westerlies. And then we have, again, the trade winds called the polar easterlies, because they're going to move the air in a westward direction with the wind coming from the east. Now, a little tricky. If you end up at a boundary, if I'm in a boat, it only has sails, I can't motor through anything, it can be very difficult when I'm at a boundary between my cells, especially the equator, because these are so powerful on either side. That means that the area in between them is very dull. These are actually called the doldrums down here, the equatorial doldrums, because there was no movement. You would be stuck in this part of the ocean for days, for weeks, because there's no cells providing that wind. We have a similar one between at 30 here, where we call that the horse latitudes, and again up at 60 degrees, known as the polar front. So anytime that ships would get stuck at these boundaries, they were stuck in that area. They were not moving because there's very little wind. I hope this gave you a better perspective of how all the air moves around our Earth, which will help us when we get started into weather next. Awesome.